From the earliest days of human imagination, the desire to vanish from one place and appear in another has haunted myths, religions, and stories told by firelight. Ancient cultures spoke of gods and heroes who stepped across vast landscapes in the blink of an eye, covering what would take mortals weeks or months of perilous travel. In tales passed down through centuries, wizards and shamans transported themselves by sheer will, appearing suddenly at the edge of a battlefield, or vanishing from sight only to emerge on distant shores. For the human mind, trapped within a body that must walk step by step across the earth, the thought of instantaneous movement was irresistible. It meant freedom from obstacles, liberation from the chains of distance, and a triumph over the slow ticking of time. As civilizations advanced, this dream did not vanish. Instead, it adapted. In the Middle Ages, alchemists whispered of powders that could make a person dissolve into air and reassemble elsewhere. Stories of saints often carried with them miraculous journeys across impossible spans, as if holiness itself bent the rules of travel. In literature, fairy tales endowed enchanted rings or cloaks with the ability to bring their wearer instantly to safety or deliver them to a longed-for land. Always the same theme repeated: the breaking of distance, the denial of the ordinary limitations of space and time. By the age of exploration, when the planet suddenly seemed both enormous and shrinking under the sails of great ships, the dream only intensified. The wider the world appeared, the more humans yearned to compress it. The act of traveling was costly in time, in danger, and in endurance. How much more glorious it would be, people thought, if one could simply step through an invisible doorway and arrive on the far side of the ocean. The fantasy was more than convenience. It was a symbol of ultimate control over nature. To move across the world at will meant no barrier could stand against human intention. When the age of science fiction dawned in the 19th and 20th centuries, teleportation became one of its most dazzling promises. Writers described machines that dissolved matter into pure information and rebuilt it elsewhere. Star Trek brought this vision into homes around the world, showing ordinary people being shimmered into patterns of light and then materializing on alien planets. The transporter became more than a fictional device. It became a cultural symbol of progress, of adventure, of a future where humanity had finally conquered the tyranny of distance. The phrase, "beam me up," entered language itself, an almost casual shorthand for the ultimate wish to defy space. What makes teleportation so uniquely magnetic to the imagination is not only its spectacle, but its intimacy. Faster than light travel might whisk a spaceship to another star, but teleportation promises that you personally can be lifted out of your surroundings and placed elsewhere, intact and immediate. It speaks to a human desire older than science, older even than story. It is the craving to be unbound, to escape the slowness of walking, sailing, or even flying, and to leap as thought itself leaps. Thought does not crawl from one place to another, it simply arrives. In dreams, we are never delayed by distance. We are always already where we need to be. Teleportation is the dream of thought made real in the physical world. Yet for all its enchantment, the gap between fiction and reality yawns wide. The human body is not a simple object to be whisked away like smoke. It is a vast assembly of atoms, arranged in patterns of breathtaking complexity. The idea of disassembling this orchestra of particles and reassembling it without error has long seemed impossible. And so, even as we thrill at images of shimmering beams carrying explorers across galaxies, science has had to remain sober. The reality of nature resists our fantasies. Physics does not yield easily to the longings of the imagination. But then came the revolution of the 20th century. At the smallest scales of nature, beneath the world of chairs and planets and familiar machines, another set of rules awaited discovery. These rules belong not to ordinary matter, but to the strange, counterintuitive domain of quantum mechanics. Here, particles do not behave like tiny billiard balls bouncing through space. They act like waves, like probabilities, like superpositions of many possibilities at once. At this scale, information about a particle becomes as real as the particle itself. And in this strangeness, new possibilities emerge, possibilities that echo the age-old dream of teleportation. Quantum mechanics offers the first scientifically sound path to the concept of teleportation. Not teleportation of bodies, not the instant transport of physical mass across the universe, but teleportation of information. It is not matter itself that leaps, but the state of matter, the delicate quantum description that makes one particle unique. And in this lies the seed of something extraordinary. For if the state of one particle can be transferred to another at a distance, then in some profound sense, that particle has been teleported. The journey from myth to physics begins here, in the shimmering uncertainty of the quantum world. The human imagination has carried teleportation as a story for millennia. Now science, for the first time, whispers that the dream may not be entirely beyond reach. The next chapter of this journey belongs not to wizards, not to starships, but to the most mysterious link in all of physics, a phenomenon Albert Einstein once dismissed as spooky action at a distance. It is called entanglement, and it is the thread on which the possibility of teleportation hangs. When we peel back the layers of the human desire for teleportation, we begin to see that it is more than a longing for convenience. It is not simply about reaching destinations faster or bypassing the frustration of crowded highways and long flights. At its core, the dream carries with it an emotional weight. Distance is not only physical, but psychological. The miles that separate loved ones, the oceans that keep families apart, the years consumed by slow voyages, all become metaphors for the barriers between people and their aspirations. Teleportation is the promise of a universe without separation, where presence itself becomes a choice rather than a limitation. Even the language of human yearning reflects this desire. We say we wish to be in two places at once. We dream of escaping to faraway islands with a thought. We use the word instant as if it were a kind of magic incantation. Our myths and stories reveal a deep truth. Humans do not accept distance as natural. We tolerate it, but we rebel against it in imagination. That rebellion has powered inventions before. The same impatience with slowness gave birth to the wheel, to sailing vessels, to locomotives, to airplanes, to rockets. Each leap in technology has been a defiance of geography. Teleportation represents the final defiance, the erasure of geography itself. This defiance was captured most vividly by the culture of the 20th century. Star Trek presented teleportation not as a rare miracle, but as an everyday utility, as casual as a car ride. The transporter room, with its glowing platform and calm commands, suggested a future where distance is irrelevant. The effect on audiences was not only excitement, but a subtle shift in expectation. Teleportation was no longer a fantasy of magic, but a potential technology. A thing engineers might someday invent if only the mathematics and machines could be mastered. Science fiction blurred into a forecast. What had once been sorcery became the promise of science. Yet this same century gave us a deeper lesson, hidden within the equations of physics. For while human imagination leaped toward teleportation, science revealed the true difficulty. If a single human being contains on the order of 10 to the power of 28 atoms, then teleporting a body means recording the state of each one, transmitting that colossal amount of information, and rebuilding the structure without error. Even if each atom could be mapped in a billionth of a second, the time required to scan an entire body would dwarf the age of the universe, Worse still, the act of measuring quantum states destroys them. The precision required is not just technologically out of reach, it is conceptually forbidden by the very laws of quantum physics. This is the gap between fiction and reality. Fiction tells us we can dissolve into patterns of light and reappear elsewhere. Physics tells us that such a process would require a godlike mastery over information, a mastery that shatters against the uncertainty principle. The human dream seems to strike the wall of nature itself, and yet, even here, the story does not end. For while physics blocks the transporter beam of Star Trek, it reveals something else, something subtler, and perhaps even stranger. The 20th century was also the century of quantum mechanics. Out of the debates between Einstein, Bohr, and their contemporaries emerged a picture of nature unlike anything previously imagined. In this picture, particles can exist in superpositions, occupying many possibilities at once until observed. They can tunnel through barriers that should be impossible. Most astonishing of all, they can become entangled. When two particles are entangled, their states are no longer separate. A measurement of one instantly affects the other, no matter how far apart they may be. This connection, invisible and instantaneous, became a puzzle so profound that even Einstein recoiled, dismissing it as a spooky action at a distance. For decades, entanglement was treated as a paradox, a strange side effect of equations, perhaps nothing more than a mathematical trick. But experiments would eventually prove otherwise. Entanglement is real, measurable, and as bizarre as the equations predict. In this discovery, the human dream of teleportation found its first scientific anchor. Perhaps one cannot dissolve matter into light, but perhaps one can use the invisible thread of entanglement to move the very essence of a particle from one place to another. Perhaps, hidden in the quantum fabric of the universe, nature itself has left a loophole. The irony is rich. Fiction promised teleportation as an almost casual technology. Physics revealed it as impossible on the scale of matter. Yet the same physics, digging deeper, uncovered a phenomenon that resembles teleportation more closely than anything previously imagined. The dream survives, transformed. Instead of transporting flesh and bone, it transports quantum states. Instead of vanishing bodies, it transfers the information that defines them at their most fundamental level. For those who hope to beam across the stars, this may feel like disappointment. But for those who seek truth, it is more wondrous than fiction. For here, the universe whispers that reality itself is more connected than it appears. This is why teleportation has remained so gripping. It is not only the drama of instant travel, it is the revelation that nature may contain mysteries, even stranger than our imaginations. The human dream of teleportation is not only a fantasy projected into the future, it is a mirror of the universe, reflecting something hidden within the rules of existence itself. We do not dream randomly. Our dreams often shadow truths not yet uncovered. The story of teleportation is not the story of conquering technology in the 21st century. It is the story of a human longing that collides with physics, and in colliding, reveals the strange depths of quantum reality. If distance is a barrier, entanglement is the first crack in the wall. And so, at the close of this dream's first chapter, we find ourselves on the threshold. The myths of old fade. The transporter beam flickers, and in its place, the shimmering possibility of entanglement begins to glow, hinting that teleportation may be less a fantasy and more a discovery waiting to be grasped. If teleportation has always been a dream of liberation from distance, then entanglement represents the first scientific bridge between desire and reality. The myths of instantaneous travel spoke of gods and sorcerers, but the mathematics of quantum physics speaks of particles and states, probabilities and measurements. The difference is profound, yet the resonance remains. Humans long imagined a hidden thread that could carry them across the world in an instant. Physics has revealed that a hidden thread truly exists, only it links particles rather than people. And if particles can be linked, perhaps someday systems of particles, even enormously complex ones, might be bound by the same thread. It is important to pause and reflect on why this matters so deeply. Humanity has always invented technologies to overcome its frailties. The wheel overcame the limits of legs. The sail conquered the winds and opened oceans. The airplane triumphed over gravity. But distance has remained the oldest and most stubborn obstacle. Even at the speed of light, signals take years to cross the vastness of space. To visit another star with current technology would require lifetimes. Against this immensity, teleportation shines as the ultimate rebellion. It is not just faster travel. It is the refusal to accept the structure of space as binding. It is the statement that thought and presence should not be chained by the slow crawl of matter. Of course, the sober truth is that matter cannot simply be beamed across the cosmos like the shimmering figures on television screens. The body is too complex, and the laws of quantum mechanics too strict for such a fantasy to ever take shape. But the beauty of science is that it reshapes dreams into new forms rather than destroying them. Teleportation survives, not as fiction, but as fact, in the teleportation of quantum states. When a photon state is transferred from one location to another, without the photon itself traveling, something astonishing occurs. It is not the same as stepping onto a transporter pad, yet it is the beginning of a story that may reach farther than even fiction imagined. The human fascination with teleportation is also a fascination with connection. To teleport is to erase the separation between here and there, between self and other, between longing and fulfillment. It is not only about convenience or conquest of nature. It is about unity. It is about collapsing the walls that isolate us from one another and from the vast reaches of the cosmos. Entanglement, by linking particles in defiance of distance, speaks to that same longing. It is as if nature herself has written into the laws of physics a reminder that separation is not absolute. This is why the idea grips us so powerfully. It is not only the technology that matters, but the symbolism. A world where teleportation is possible is a world where boundaries dissolve. The child dreaming of reaching the stars without delay, the parent wishing to embrace a child across an ocean, the explorer longing to see what lies on the other side of the galaxy. All are united by the same hunger. Teleportation is the distilled form of hope that distance can be overcome. We must accept, however, that science offers gifts in unexpected ways. It rarely delivers the exact shape of our fantasies. Instead, it transforms them. The reality of teleportation is not a shimmering beam of light, but a carefully constructed quantum protocol. It requires entangled pairs of particles, precise measurements, and classical signals. It is fragile, technical, and demanding. And yet, when the equations are carried out and the experiments succeed, the result is unmistakable. The state of a particle disappears in one place and reappears in another. That is teleportation, not of matter, but of information. And it is real. From myths whispered by firelight to equations written on blackboards, the story of teleportation is the story of humanity stretching its imagination beyond the possible. At each stage, the dream reshaped itself. From gods to sorcerers, from alchemists to science fiction writers, and now from physicists to engineers, the vision endures. And now, for the first time, the dream rests on a foundation of fact. Quantum mechanics, with all its strangeness, provides the first genuine tool for realizing what once seemed pure fantasy. This is the transition. The dream of teleportation has passed through story and myth. It has collided with the sobering walls of physics. And now, it finds itself reborn in the strange world of quantum states. What follows is not speculation, but experiment. The next chapter belongs to entanglement itself, the strangest connection in nature, and the foundation upon which the first real steps toward teleportation are being taken. In the early decades of the 20th century, physics was turned inside out by the discovery that nature does not obey the tidy rules we once assumed. The laws of Newton had guided us for centuries, describing planets, pendulums, and projectiles with precision. But when physicists looked closer, probing atoms and the particles within them, they found a world governed not by certainty, but by probabilities. It was in this strange quantum landscape that one of the most haunting phenomena emerged, a phenomenon that would come to define the very possibility of teleportation. It was called entanglement. To describe entanglement, imagine two particles born together in the same event, like twins emerging from a single source. Once created, their fates are mysteriously linked. If one particle is measured, its properties snap into place, and instantly, the other particle's properties respond, no matter how far apart the two may be. It is as if the universe itself conspires to keep them connected, as if an invisible thread binds them across space. This is not simply a metaphor. It is a measurable fact, one that has been confirmed again and again by experiment. Albert Einstein, who helped build the foundations of quantum mechanics, recoiled from this implication. To him, physics should be local, meaning that events in one place should not instantly affect events elsewhere. He believed that the universe must obey some deeper set of hidden rules that would explain away the strangeness. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, wrote a famous paper now known as the EPR paradox. They argued that quantum mechanics must be incomplete, that there must exist hidden variables determining the behavior of particles, variables that would restore the common sense notion of locality. Einstein dismissed entanglement with a phrase that has echoed ever since. He called it spooky action at a distance. Yet physics has a way of confronting us with reality, whether we are ready for it or not. Over the decades that followed, experimentalists devised ingenious ways to test whether entanglement was real or an illusion. They designed tests now known as Bell experiments, named after the physicist John Bell, who in 1964 showed that no hidden variable theory could reproduce all the predictions of quantum mechanics. His inequality provided a sharp dividing line. If quantum mechanics was right, then entangled particles would produce correlations that no local hidden theory could match. When those experiments were performed, first with photons in the 1970s, and increasingly refined through the late 20th and early 21st centuries, the results were clear. Again and again, entangled particles showed correlations that defied any classical explanation. No signal could have passed between them, yet their behaviors were linked. The spooky action was not an illusion. It was a fact of nature. The implications are staggering. Entanglement means that information about a system cannot always be confined to one place. Instead, it can be shared across distance in a way that makes the parts inseparable. It is as if reality itself refuses to be divided cleanly. A pair of entangled particles does not consist of two independent objects, but of one extended state, spread across space. When we measure one, we do not reveal a hidden property. We collapse the entire state, binding both particles in a single act of observation. For centuries, we thought of space as a stage upon which objects moved independently. Entanglement suggests that the stage itself can connect objects in ways we had never imagined. It whispers that separation is not absolute, that there are threads of correlation woven into the fabric of the universe. And it is precisely these threads that make quantum teleportation possible. Einstein's discomfort with entanglement was understandable. For a man who had revealed that time and space themselves could bend, even he balked at the idea of instantaneous influence across distance. His theory of relativity insisted that no signal could travel faster than light, that causality itself would collapse if information leapt instantly from one place to another. Yet entanglement seemed to mock that limit. If two particles could respond to each other with no delay, did this not imply faster than light communication? Einstein could not accept it. He was convinced that quantum mechanics was only a temporary approximation of a deeper theory yet to be discovered. But the universe does not bend to our preferences. Experiments showed that entanglement was real, and more intriguingly, that it did not violate relativity. The catch is subtle, but crucial. Entanglement correlations appear instant, yet they cannot be used to send a usable signal faster than light. The outcomes are random, unpredictable, until compared through a classical channel. Only when the results are brought together, slower than light, does the hidden pattern reveal itself. Nature allows connection, but guards causality. It gives us a glimpse of unity across space, but refuses to let us cheat the cosmic speed limit. What makes entanglement so strange is that it resists classical pictures. If one imagines particles carrying hidden instructions from their moment of creation, those instructions would have to account for every possible measurement choice and outcome, a requirement that grows impossible to reconcile with the observed violations of Bell's inequality. No local script can explain what happens. Instead, quantum theory tells us that the particles share a single state that exists beyond ordinary space, a mathematical object that spans both particles at once. The separation we see is an illusion of perspective. Beneath it lies an indivisible whole. In the laboratory, entanglement is not merely philosophy. It can be created, measured, and even manipulated. Physicists entangle photons by sending them through special crystals that split beams of light into pairs with correlated polarizations. They entangle atoms by cooling them to near absolute zero and allowing their quantum states to merge. They entangle ions trapped in electromagnetic fields, coaxing them into a shared vibrational mode. Each of these experiments proves the same point. Entanglement is not a curiosity, it is a resource, a kind of currency in the quantum world. This resource has consequences. With entanglement, one can perform feats that classical physics cannot. Quantum cryptography uses it to guarantee secure communication, for any attempt at eavesdropping disturbs the delicate correlations. Quantum computing relies on entanglement to link qubits into webs of computation far more powerful than classical bits. And most striking of all, quantum teleportation uses entanglement to transfer the state of a particle from one location to another. Without entanglement, teleportation would be fantasy. With it, teleportation becomes experiment. The path from Einstein's derisive phrase, spooky action at a distance to today's precise laboratory control of entangled states, is one of the most remarkable journeys in science. It reveals the stubbornness of reality, refusing to be tamed by intuition, and the creativity of human minds, willing to test even the strangest predictions. Entanglement has shifted from paradox to tool, from discomfort to foundation. And in that transformation lies the seed of teleportation. The deeper we look, the more entanglement challenges our notions of separateness. It suggests that particles created together remain part of one extended system, no matter how far they drift apart. This does not mean they exchange signals in the ordinary sense. It means the concept of individuality, of particles as isolated objects, breaks down. The universe is more holistic than our instincts suggest. Where we see parts, nature sometimes insists there is only one. It is this strangeness, this refusal of the universe to let go of its hidden unity, that will allow us to understand how teleportation of quantum states is possible. The story of teleportation cannot begin with machines or technology. It must begin with this connection, this invisible bond that makes distant particles dance in unison. Only by embracing the reality of entanglement can we begin to see how information itself might be moved without moving matter, how presence might leap without travel. The recognition that entanglement is real and usable has reshaped physics into something both practical and profound. It is no longer enough to treat it as a paradox whispered in theoretical discussions. Laboratories across the world now generate entangled pairs daily, shipping them through fiber optic cables, bouncing them off satellites, or storing them in quantum memories chilled to near absolute zero. What was once dismissed as a ghostly curiosity is now a cornerstone of quantum technology. Yet entanglement remains unsettling because it blurs the boundary between what is here and what is there. If a pair of photons are entangled, then measuring one reveals something about the other instantly, even if they are separated by kilometers. In one sense, nothing has traveled. No particle has darted across the space in between. In another sense, everything has traveled, for the information that defines their relationship is spread across both, inseparable until collapsed by measurement. It is not that one influences the other at a distance. It is that they were never truly separate to begin with. This forces us to reimagine the nature of reality itself. If space and time are the framework of the universe, entanglement suggests there are deeper connections beneath them. Some physicists speculate that entanglement is not merely a feature of quantum mechanics, but the very fabric out of which space-time itself is woven. According to ideas such as ADS-CFT duality, the geometry of space might emerge from patterns of entanglement, as if reality is stitched together by invisible correlations. If that is true, then the dream of teleportation is not a rebellion against nature, but a discovery of its deepest law, a recognition that the universe itself thrives on hidden unity. The experiments that confirm entanglement are often simple in design, yet profound in implication. Two detectors placed kilometers apart record photons arriving from a shared source. Each detector chooses at random how to measure its photon. The results, when compared later, show correlations too strong to be explained by any local script. These experiments have been repeated on mountains, across cities, even between ground stations and orbiting satellites. Each time the verdict is the same. Nature does not respect locality as we once thought. Entangled particles behave as if distance does not matter. And yet, the universe preserves its balance. No matter how strange the correlation, no usable message can be sent instantly. Entanglement offers connection without communication, unity without signal. It is a reminder that physics gives gifts, but also imposes limits. The cosmos teases us with glimpses of impossible freedom, but guards the gates of causality. The human dream of teleportation may be awakened by entanglement, but it will not be a simple dream of faster than light travel. It will be something subtler, something that redefines what we mean by movement and information. To stand at the threshold of quantum teleportation is to accept this paradox. On one hand, entanglement shows that particles can share states across distance. On the other, it insists that we cannot use this to defy relativity. What we are left with is not disappointment, but wonder. For in the strangeness of entanglement lies a tool more powerful than any classical technology, a tool that allows us to move the essence of a particle from one place to another without moving the particle itself. Einstein once scoffed at spooky action at a distance. Today, physicists embrace it as the foundation of quantum information science. Without it, teleportation would remain in the realm of myth and fiction. With it, we stand at the dawn of a new era where information itself can leap across space, bound not by matter, but by correlation. The next step is to see how this principle is harnessed, to watch as entanglement is turned into a protocol that transfers quantum states. That step will take us into the heart of quantum teleportation itself, where the dream of instant presence becomes a physical process. When the word teleportation is spoken, the imagination leaps to visions of bodies dissolving into beams of light and reassembling elsewhere. The truth revealed by physics is stranger and more subtle. Quantum teleportation does not move matter. It does not transport particles from one location to another, like freight carried invisibly through the air. Instead, it transfers the most fragile and essential element of a particle, its quantum state. To understand this, one must accept that in quantum mechanics, the state is everything. A quantum state describes not only what a particle is, but what it could be, the full spectrum of probabilities that exist until measurement collapses them into a single outcome. Unlike classical information, which can be copied and stored without limit, a quantum state is unique and delicate. The uncertainty principle forbids us from measuring it completely without disturbing it. This fragility seems to doom the idea of moving a state from one particle to another. But entanglement provides a loophole. By using the invisible connection between entangled pairs, it becomes possible to transfer a state without ever measuring it directly. The process requires 3 ingredients. First, a particle whose state we wish to teleport. Second, a pair of entangled particles shared between the sender and the receiver. Third, a channel of classical communication that can transmit the results of certain measurements. The sender, often called Alice in the traditional storytelling of quantum theory, holds the unknown particle and one member of the entangled pair. The receiver, called Bob, holds the other entangled particle. Alice performs a special joint measurement on her 2 particles, a measurement that projects them into what are called Bell states. These are maximally entangled states, the 4 fundamental patterns into which 2 quantum bits can be locked. By carrying out this measurement, Alice entangles her unknown particle with her part of the shared pair, and in doing so, destroys the original state. But at the same instant, the information of that state is imprinted onto Bob's particle, waiting to be revealed. Here lies the beauty and the precision of the process. Alice's measurement gives her a result that can be one of 4 possibilities. She cannot control which outcome occurs, but whichever it is, it tells her exactly what operation Bob must perform on his particle to recover the original state. She sends her result to Bob through a classical signal, obeying the speed limit of light. When Bob applies the corresponding operation, his particle becomes an exact replica of the state that Alice destroyed. The state has been teleported. No particle has crossed the distance between them. No matter has flown through space. Yet the defining information, the quantum identity of one particle, has vanished in one location and reappeared in another. The original is gone. The copy is perfect. The transfer is complete. This is quantum teleportation, a triumph of ingenuity that uses the most mysterious feature of physics to accomplish something that once seemed impossible. The process may sound abstract, but it is grounded in concrete mathematics. The Bell measurement is not a fantasy, but a well-defined operation in the algebra of quantum mechanics. The requirement of entanglement is not a trick, but a resource that can be created in laboratories. The need for classical communication explains why teleportation cannot be faster than light, for without Alice's signal, Bob cannot know how to interpret his particle. Each step is precise, demanding, and real. What makes this remarkable is not only that it works, but that it respects every known law of physics. Information is not copied, which would violate the no-cloning theorem. Instead, the state is destroyed in one place and reborn in another. Causality is preserved, for classical signals still travel at or below the speed of light. And yet, the outcome defies our common sense. We are accustomed to movement requiring motion, to transfer requiring transit. Here, the essence of a quantum particle leaps across space without traversing the distance in between. It is as close as reality comes to the magic of fiction. The first time scientists proposed this process, it sounded almost like a joke. In 1993, Charles Bennett and colleagues published a paper that gave a recipe for quantum teleportation. At that time, the very term carried the weight of science fiction, and the image of shimmering transporters overshadowed the sober mathematics behind it. Yet Bennett and his team were precise. They showed that by using entanglement and a limited amount of classical communication, the exact state of a quantum system could be transmitted from one place to another without ever being measured directly. The scheme was elegant and airtight. It did not violate relativity, it did not break the no-cloning theorem, and it did not require faster than light signaling. What it required was entanglement, measurement, and communication. For a while, it remained theory, a clever idea written in the language of mathematics. But theory in physics has a way of becoming experiment. Within just a few years, laboratories began attempting to put Bennett's vision into practice. In 1997, a team led by Anton Zeilinger in Austria achieved the first successful demonstration of quantum teleportation using photons. They created pairs of entangled photons, prepared a third photon in an unknown state, and carried out the delicate measurement. The result was astonishing. The state of the original photon appeared in a distant photon, transferred without the particle itself making the journey. The process worked. Teleportation was no longer just a word from fiction. It was a fact of laboratory physics. The demonstrations that followed grew increasingly sophisticated. Photons were teleported across greater distances, through optical fibers, across open air, even between islands. Each success confirmed the same principle. The state of a quantum system could be relocated by destroying it in one place and reconstructing it in another, guided by entanglement and classical signals. The beauty of the process lies in its fidelity. The teleported state is not an approximation, but an exact reproduction, limited only by experimental imperfections. This is not to say the process is easy. Performing a Bell state measurement requires precision at the edge of experimental possibility. Maintaining entanglement is notoriously difficult, for interaction with the environment causes decoherence, the gradual loss of quantum information. Classical communication must be synchronized with quantum operations, demanding careful timing. Every element requires finesse. Yet, despite these challenges, the principle has been proven beyond doubt. The most profound aspect of quantum teleportation is that it alters our understanding of what it means to move information. In classical communication, a message is copied, encoded, and sent. In teleportation, there is no copy. The original vanishes as the new one is created. It is a transfer without duplication, a flow without residue. In some sense, it echoes the very structure of quantum reality, where outcomes arise not as replications, but as unique events. The process also highlights the interplay between the strange and the ordinary. Without entanglement, teleportation is impossible. Without classical communication, it is incomplete. It is as though nature insists that we must use both the mysterious and the mundane. The quantum provides the invisible thread, but the classical provides the anchor. Only by weaving the two together does teleportation succeed. By the end of the 20th century, what began as a theoretical exercise had become an experimental reality. The dream of teleportation was no longer confined to myths or television screens. It had entered the laboratory, built not from fantasy, but from equations and photons. The next question was inevitable. If teleportation works for single particles, could it be scaled to larger systems? Could atoms, molecules, or even more complex states be transferred in the same way? And if so, how far could this principle go? The success of the first teleportation experiments was more than a technical achievement. It was a philosophical milestone. For centuries, the dream of instant movement had been confined to myth and imagination. Now, in the quiet light of a laboratory, a photon state had truly vanished from one place and appeared in another. This did not mean bodies were beamed across space, but it did mean that nature allowed a kind of teleportation, one rooted not in fantasy, but in the laws of physics themselves. Physicists quickly realized that teleportation is not an exotic trick, but a fundamental process with profound implications. It showed that entanglement could serve as a channel for moving quantum information. It demonstrated that the no-cloning theorem, which forbids perfect copying, is not an obstacle, but an essential feature. By destroying the original, teleportation respects the integrity of quantum mechanics. It transforms the paradox of fragility into a method of transmission. This opened new avenues of research. If quantum states could be teleported reliably, then they could be used as building blocks for larger networks. Quantum computers, envisioned as machines that harness superposition and entanglement for calculation, would one day need to share information across distances. Quantum teleportation offered a method for doing so without loss of fidelity. Quantum cryptography, seeking absolute security in communication, could be strengthened by teleportation protocols that ensured information traveled without interception. Slowly, teleportation began to shift from curiosity to necessity. The mechanics of the process, though invisible to the naked eye, carry a dramatic quality when imagined in detail. Picture Alice preparing an unknown photon, fragile and unmeasured. She brings it together with one half of an entangled pair. With delicate instruments, she performs a Bell measurement, entangling the photon with her particle and erasing the original state. In that instant, the state is no longer anywhere, yet it is not lost. Across the laboratory, Bob holds his entangled photon, seemingly unchanged. Then Alice sends her result through a classical channel, perhaps a simple pulse of light or an electrical signal. Bob receives the message, performs the instructed operation, and suddenly his photon becomes the original. The state has been reborn. No particle has traveled, but the identity has leapt. For the outside world, the effect is invisible, but for the physicist, it is breathtaking. It is as though the rules of reality have been bent just enough to allow a miracle, and yet the miracle obeys every law. The elegance of teleportation lies in its paradoxical nature. It feels like cheating, but it is perfectly legal. It feels like magic, but it is mathematics. By the dawn of the new millennium, teleportation had become one of the crown jewels of quantum information science. It had been tested with photons, refined with ions, and debated in conferences and journals. Each success drew new questions. Could the distance be extended? Could the fidelity be increased? Could the process be scaled to more complex systems? The experiments that followed would chase these questions, pushing teleportation out of the laboratory and into the open world. The transition was clear. Quantum teleportation was no longer simply a proof of principle. It was becoming an engineering challenge, a race to harness entanglement over greater distances and under harsher conditions. If it could be done reliably, the foundations of a quantum internet would be laid. The next chapter of the story would not unfold in theory, but in practice, as photons were pushed through fibers across cities and even between Earth and orbiting satellites. The stage was set for teleportation to leave the confines of the laboratory and step into the real world. The first demonstrations of quantum teleportation were triumphs of principle, proving that the impossible could in fact be done. But principles are not enough. For teleportation to become more than a laboratory curiosity, it must work under real conditions, across meaningful distances, and with reliability that does not vanish under the slightest disturbance. The story of quantum teleportation therefore moved from delicate benchtop experiments to ambitious trials carried out in cities, across mountains, and even between the Earth and space itself. In 1997, Anton Zeilinger and his collaborators in Vienna pushed teleportation beyond theory for the first time. They took photons entangled through nonlinear crystals and carried out the precise Bell measurements needed to teleport the state of one photon to another. The distances involved were small by everyday standards, but they marked the first time a quantum state had been transferred in practice. The demonstration was like the first flight of the Wright brothers. The distance covered was not the point. The point was that flight itself had been achieved. Over the next decade, researchers refined the process and began to stretch the distances. One of the earliest goals was to see whether teleportation could survive through optical fibers, the same channels that carry much of the world's internet traffic. Photons traveling through fibers are subject to losses and scattering, and entanglement is fragile in the face of such disturbances. Yet progress was made. Teams succeeded in teleporting quantum states over several kilometers of fiber, proving that the principle could in fact coexist with the technology already crisscrossing our planet. Experiments soon moved beyond the laboratory into open air. In China and Europe, photons were entangled and then sent through telescopes across city rooftops and even between islands separated by water. These experiments tested teleportation under the interference of atmosphere, weather, and distance. One of the most famous achievements occurred in the early 2000s, when Zeilinger's group demonstrated teleportation across the Danube River, sending photons through open-air channels and reconstructing their states with remarkable fidelity. Each such success pushed the boundary of what was possible and built confidence that teleportation was not restricted to carefully shielded laboratories. By the 2010s, Chinese researchers under the leadership of Jianwei Pan pushed the frontier dramatically further. In a series of experiments, they teleported quantum states over distances of more than 100 kilometers using free space optical links. The precision of their instruments, the stability of their systems, and the strength of their entanglement made these feats possible. These distances are not trivial. To hold entanglement across tens of kilometers is to defy the natural tendency of decoherence to erase quantum information. It requires engineering of the highest order, with lasers locked in frequency, telescopes tracking photons with sub-millimeter accuracy, and detectors sensitive to the faintest pulses of light. These advances prepared the stage for one of the most ambitious experiments in physics, the use of satellites to test entanglement and teleportation on a planetary scale. The Chinese satellite Mikius, launched in 2016, carried instruments designed to create and distribute entangled photons between ground stations separated by more than 1,000 kilometers. For the first time in history, entanglement was verified across distances measured not in city blocks or rivers, but in spans comparable to entire nations. Teleportation of photons between ground and satellite was achieved, demonstrating that quantum information could leap across space on a global scale. The triumph of the Mikius satellite was more than a scientific achievement. It was a demonstration that teleportation could become a backbone of future technology. Until then, teleportation had been confined to fibers in the ground or short distances through air. Mikius showed that quantum states could be sent between Earth and orbit, bridging distances of more than 1,000 kilometers with fidelity that stunned even seasoned physicists. Photons generated in space and distributed to widely separated ground stations remained entangled, and their states could be teleported from one location to another. It was as if the planet itself had become a stage for the drama of quantum mechanics. What makes these experiments extraordinary is not only the distances involved, but the precision required. To distribute entangled photons between Earth and a satellite, telescopes must track beams across hundreds of kilometers through the shifting turbulence of the atmosphere. The photons themselves are faint, their survival rate low. Detectors must capture single photons with nanosecond timing. filtering out background light from the stars and cities below. The fact that any signal arrives at all is astonishing. The fact that entanglement survives the journey is nothing short of breathtaking. Yet each experiment carried more than technical meaning. It carried symbolic weight. Humanity has long dreamed of networks that bind the globe together. The telegraph once shrank continents to seconds. The internet shrank them to instants. And now quantum networks promise a new kind of unity. Teleportation sits at the heart of that vision. If photons can carry entangled states across mountains, rivers, and space itself, then one can begin to imagine a planetary web of entanglement, a quantum internet where teleportation is routine. The experiments on Earth also revealed the practical limits of the process. Entanglement decays as distance grows. Photons are lost in fibers, scattered in air, absorbed by clouds. Classical signals, required to complete the teleportation protocol, add delays. These challenges forced researchers to innovate. They developed quantum repeaters, devices that extend entanglement by linking shorter segments into longer ones. They engineered better detectors, capable of capturing photons with higher efficiency. They built adaptive optics to correct for atmospheric distortion. Each obstacle became an opportunity to refine the craft. There is a sense of wonder in recognizing how far the field has come. In the late 1990s, teleportation over a few meters of fiber seemed astonishing. By the early 21st century, teleportation across tens and then hundreds of kilometers had been demonstrated. By the 2010s, teleportation reached from ground to orbit. The pace of progress suggests that what now seems extraordinary may soon become ordinary. The dream of teleportation is no longer confined to thought experiments or science fiction. It is written into the record of experiments, measured in laboratories, logged in journals, and validated across continents. Still, teleportation on Earth remains fragile. Each experiment requires elaborate infrastructure, precise synchronization, and conditions that are often unforgiving. Clouds can disrupt signals, vibrations can misalign optics, and thermal fluctuations can disturb detectors. To build a truly global network of teleportation will require not only scientific brilliance, but engineering resilience. It will demand systems that work not only in laboratories, but in the messy unpredictability of the real world. And yet, even with these challenges, the trajectory is clear. What began as an idea in a paper in 1993 is now an international effort, stretching across oceans and into space. Teleportation has left the blackboard and entered the world. It is no longer merely a question of whether it can be done. The question now is how far it can go. The global experiments in teleportation reveal a pattern that echoes the history of human progress. At first, achievements are modest, barely more than proof of principle, like the first steps taken by a child. Then distances grow, obstacles are faced, and gradually the extraordinary becomes routine. Teleportation followed this same arc, from the delicate measurements in Vienna to the island-hopping links across Chinese waters, from rooftop laboratories in Europe to beams of light exchanged with a satellite orbiting Earth. The journey has been a steady expansion of scale and ambition. Each new record has transformed the way physicists and engineers think about the possibilities ahead. At the heart of these successes lies a vision of the quantum internet, a network that would bind together distant laboratories, cities, and eventually continents using entanglement as its foundation. In such a network, teleportation would not be an occasional experiment, but a daily operation, moving quantum states as easily as classical bits now travel across fiber optics. The difference would be profound. Unlike classical communication, which can be copied and intercepted, quantum teleportation preserves security through the laws of physics themselves. Any attempt to eavesdrop on the process would break the entanglement and reveal the intrusion instantly. The promise of unbreakable security is one of the driving forces behind this field. But the dream extends further. If entanglement can be distributed across the globe, then it may also be extended beyond it, linking Earth with spacecraft, lunar outposts, or even missions to Mars. Teleportation could become the lifeline of quantum communication across the solar system. It would not carry human bodies, but it would carry the information needed to coordinate machines, to synchronize clocks, to ensure secure links across cosmic distances. The experiments on Earth are the first rehearsal for such possibilities. Each photon sent across a river or a satellite link is a step toward a universe where distance is less absolute than it once seemed. The challenges remain daunting. Decoherence, photon loss, and the need for classical channels impose strict limits. The infrastructure for long-distance teleportation must be built piece by piece, with repeaters, satellites, and quantum memories forming the backbone. But the achievements already made prove that the limits are not absolute. They are barriers to be overcome, not walls that cannot be breached. The very existence of teleportation experiments on a planetary scale shows that nature allows it. What remains is to refine, scale, and integrate. Looking back, it is astonishing how quickly teleportation advanced from a paper written in 1993 to a satellite experiment spanning over 1,000 kilometers less than 3 decades later. This pace suggests that the coming decades may hold even more surprising leaps. The question is no longer whether teleportation is real, it is how it can be harnessed, expanded, and embedded into the fabric of human civilization. The story of experiments on Earth thus closes with a sense of momentum. The dream of teleportation is no longer confined to myths, nor to laboratories, nor even to short-range demonstrations. It is a planetary enterprise, stretching across nations and into orbit. The next stage of the story, however, requires us to face the limits head-on. For every success in teleportation reveals the obstacles that remain. The fragility of entanglement, the requirement of classical communication, the impossibility of faster-than-light transmission. These are the challenges that define the horizon. To move forward, we must understand those limits, and only then imagine how they might be overcome. The triumphs of teleportation on Earth and in orbit shimmer with possibility, yet beneath them lies a sobering truth. Every experiment that succeeds also illuminates the constraints written into the fabric of reality. Teleportation works, but not in the way fiction promised. It is precise, fragile, and bound by laws that cannot be ignored. To glimpse its power, one must also confront its limits. The first and most fundamental limitation is that teleportation requires entanglement. Without an entangled pair of particles shared between sender and receiver, the process cannot even begin. Entanglement is the channel, the invisible thread across which the state travels. But generating entanglement is not trivial. It requires carefully prepared sources, crystals that split beams of light, atoms cooled to near absolute zero, or ions trapped in electromagnetic fields. Once created, entanglement must be distributed, often across vast distances, where it is constantly threatened by loss and noise. If the entangled particles are disturbed by the environment, the delicate correlations collapse, the channel vanishes. This fragility brings us to the second limitation, decoherence. Quantum states are exquisitely sensitive to their surroundings. A single interaction with stray light, a vibration, or a magnetic field can destroy coherence, erasing the information that defines the state. Decoherence is not an accident, but a natural process. It is the tendency of quantum systems to become entangled with their environment, leaking their information into countless uncontrolled degrees of freedom. To preserve teleportation, One must shield particles from this fate, isolating them from the world while still guiding them through the process. It is like carrying a candle through a storm, each gust threatening to snuff it out. A third limitation is the requirement of classical communication. In every teleportation experiment, once the sender has performed the bell measurement, the outcome must be transmitted to the receiver through an ordinary signal. That signal travels no faster than the speed of light. Until it arrives, the receiver cannot complete the teleportation. This rule preserves the integrity of relativity, ensuring that no information travels faster than light. It also means that teleportation, despite its glamour, does not offer instantaneous communication. The state appears to leap across space, but the leap is incomplete without the slower thread of classical information. These three requirements, entanglement, coherence, and classical communication, form the skeleton of teleportation's limits. But there are further challenges. Fidelity, the measure of how closely the teleported state matches the original, is never perfect in real experiments. Photons are lost in fibers, detectors miss events, and measurements produce errors. Achieving high fidelity requires extraordinary precision in alignment, timing, and calibration. Even under the best conditions, imperfections creep in. Teleportation works, but always with a margin of error that must be acknowledged. Taken together, these limits remind us that teleportation is not magic. It is a process bound by the rules of quantum mechanics, constrained by the realities of engineering, and shaped by the harshness of the environment. It can move states, but not mass. It can carry information, but not faster than light. It can connect, but only within the boundaries nature has set. And yet even in these limitations, there is wonder. For the very fact that teleportation is possible at all is astonishing. The limits do not erase the achievement. They sharpen it. They tell us that nature allows connection across space, but only in ways that preserve coherence and respect causality. The challenge of the coming decades will be to live within these limits while pushing their boundaries, to see how far teleportation can go before it bends into impossibility. The fragility of teleportation becomes clearest when we focus on decoherence. Quantum mechanics allows particles to exist in superpositions, balanced between many possibilities at once. But these superpositions are easily disturbed. When a quantum particle interacts with its environment, even in the slightest way, it becomes entangled with the countless degrees of freedom around it. This entanglement with the environment collapses the delicate state, leaving behind only classical probabilities. The coherence, the very essence of what makes quantum information special, is lost. Consider a photon traveling through an optical fiber. Along its journey, it may scatter, be absorbed, or experience subtle changes in phase as it passes through imperfections in the glass. Each interaction threatens its coherence. Over short distances, the losses can be tolerated. Over hundreds of kilometers, they become crippling. Without correction, the entangled state decays, and teleportation fails. This is why most experiments so far have been confined to limited ranges, or have relied on satellites, where photons travel mostly through empty space. For atoms and ions, the problem is even more severe. To teleport their states, they must be isolated from vibrations, electromagnetic noise, and thermal fluctuations. Laboratories build elaborate traps and shields, cooling particles to near absolute zero to keep them coherent. Even then, coherence times are limited, measured in milliseconds or seconds before the environment wins. To extend teleportation to larger and more complex systems will require coherence times that last far longer. It is like trying to preserve a snowflake in the desert, requiring constant protection against inevitable melting. Another limit comes from the no-cloning theorem, one of the most profound rules of quantum mechanics. It states that an unknown quantum state cannot be perfectly copied. At first glance, This seems a barrier to teleportation, but it is in fact its saving grace. The no-cloning theorem ensures that teleportation must destroy the original state before creating the new one. This prevents duplication, which would otherwise allow paradoxes and violations of causality. It also means that teleportation is not a method of multiplying information, but of transferring it. This is why the process requires destruction in one place and rebirth in another. In practice, however, the no-cloning theorem introduces strict requirements. The measurement carried out by the sender must be perfect. Any error in that measurement means the original state is destroyed without being faithfully reconstructed. The fragility of the process is absolute. Unlike classical copying, where redundancy and backups can recover information, quantum states offer no second chance. Once lost, they are gone forever. The reliance on classical communication is another subtle but crucial limit. Entanglement creates correlations that appear instant, but those correlations cannot be used to send a message without the slower classical channel. This prevents teleportation from enabling faster-than-light communication. To some, this may feel like a disappointment, a reminder that the dream of instantaneous contact across galaxies remains out of reach. But it is also a reassurance. It means that teleportation does not break the consistency of the universe. It honors relativity, while revealing new ways to connect. These limits force creativity. Physicists design quantum repeaters to extend entanglement across larger distances. They develop error correction codes to protect fragile states. They seek new materials and techniques to hold coherence longer. Each limitation becomes a challenge, each challenge an invitation to innovation. The story of teleportation is therefore not only a tale of triumph, but also of constant negotiation with the laws of physics. It is a dance between what is allowed and what is forbidden, between what is possible now and what may be possible in the future. The limits of teleportation may appear as obstacles, yet in truth, they define the landscape in which progress must occur. By understanding these boundaries, physicists can chart the path forward. Decoherence may erase fragile states, but it also motivates the search for quantum memories, devices that can store entanglement for longer times. Losses in fibers may scatter photons, but they inspire the building of repeaters that can stitch shorter links into longer ones. The need for classical communication may delay the final step, but it forces clarity, ensuring that teleportation remains consistent with the larger structure of physical law. One of the most intriguing aspects of these limits is how they reshape the dream of teleportation itself. Fiction imagined instantaneous journeys, bodies shimmering into beams of light and appearing intact on distant planets. Physics tells a different story. Teleportation is not about matter, but about information. It is not about breaking the speed of light, but about working within it. It is not about perfect copies, but about transfers that destroy the original and rebuild it elsewhere. The dream survives, but in a form that is subtler and perhaps more profound. This subtlety becomes clearer when we reflect on what teleportation actually achieves. When a quantum state is teleported, it is not that something has moved faster than light, nor that a signal has bypassed space. It is that the identity of a particle has leapt across distance, carried invisibly by entanglement, and revealed only when guided by classical communication. It is as if nature allows us to slide information across the surface of reality, while still respecting the deeper currents of causality. The miracle is real, but it is bounded. The challenge of the future is to push against these boundaries without breaking them. Physicists are developing protocols to extend entanglement across global networks, designing quantum repeaters that can refresh and extend coherence, and exploring new materials to hold quantum states longer. Satellites like Mikius, show that the atmosphere can be conquered. Laboratories working with trapped ions and cold atoms show that matter itself can be teleported in principle. Each success expands the field of the possible, even as the limits remain visible on the horizon. There is also a philosophical lesson in these limits. They remind us that teleportation is not a trick to escape the rules of the universe. It is a discovery within those rules. The speed of light remains absolute. The no-cloning theorem remains inviolable. Decoherence remains a constant threat. Yet within these constraints, teleportation is real, astonishing, and usable. Nature does not give us everything we dream of, but it gives us enough to reshape what we thought possible. As the chapter of limits closes, the story of teleportation does not end in disappointment. It ends in determination. The obstacles are not walls but challenges, invitations to refine technology and deepen understanding. The next step is to ask whether teleportation can move beyond photons into more substantial systems, atoms and molecules that carry richer information and resemble the matter of which we ourselves are made. To face that question is to step once again into the unknown, carrying with us both the triumphs and the limits of what has been learned. For many years, photons have been the workhorses of teleportation. They are light itself, easy to generate, able to travel long distances, and relatively simple to manipulate. Photons have carried quantum states through fibers, across cities, and even between Earth and satellites. But photons alone cannot build the future of teleportation. To move beyond demonstrations into systems that store and process information, scientists must learn to teleport not only light, but matter itself. The next chapter in this story belongs to atoms, ions, and molecules, the very building blocks of the material world. The leap from photons to atoms is immense. Photons are fleeting, passing through detectors in nanoseconds, while atoms can be trapped, cooled, and manipulated for long periods. Teleporting the state of an atom is therefore not just a feat of physics, but a step toward practical quantum memories, systems that can hold quantum information until it is needed. Such memories are essential for building networks and computers that rely on teleportation as more than a one-time trick. One of the earliest breakthroughs came with trapped ions. Physicists developed techniques to hold individual ions in electromagnetic fields, cooling them with lasers until their motion slowed to near stillness. In this delicate environment, the internal states of the ions could be controlled with exquisite precision. In 2004, a team succeeded in teleporting the quantum state of one ion to another within a single trap. The experiment was a triumph, proving that matter itself could undergo teleportation. The ion did not move, but its quantum identity was transferred. Experiments with neutral atoms followed, often using ensembles of atoms cooled to form collective quantum states. In such systems, the information is not stored in a single atom, but in the shared state of many, like a chorus singing in unison. Teleporting states between these ensembles open new possibilities for quantum memories. Instead of fleeting photons, these systems could hold information long enough to form the backbone of communication networks. Teleportation became a tool not only for demonstration, but for architecture. The significance of these advances cannot be overstated. By teleporting the states of atoms and molecules, scientists showed that teleportation could reach into the realm of matter. This was not yet the teleportation of complex structures, let alone living beings, but it was a step away from the ephemeral and toward the substantial. Atoms and ions are the same particles that form the molecules of life. To move their states is to move closer, however distantly, to the possibility of teleporting larger and more complex systems. Yet with these achievements came new challenges. Atoms are heavier than photons. more easily disturbed by their environment. Holding them in traps requires constant control. Cooling them demands elaborate systems of lasers and magnetic fields. Decoherence remains the ever-present enemy. Each experiment requires conditions more like an orchestra of precision instruments than a simple laboratory setup. Teleportation at this level is not casual. It is intricate, fragile, and immensely demanding. Still, the proof is there. Photons may have carried teleportation across the globe, but atoms and ions show that teleportation can extend to the very stuff of matter. They mark a step toward the future, where teleportation may connect not only flashes of light, but the enduring structures that make up our world. The teleportation of atoms and ions opened a doorway to one of the most urgent goals of quantum information science, the development of quantum memories. A photon may carry information across vast distances, but it cannot linger. It races onward at the speed of light, vulnerable to loss and scattering. To build a network that spans continents or planets, information must sometimes pause, waiting for synchronization or routing. This is where atomic systems shine. Atoms can be held in traps, their quantum states preserved for milliseconds, seconds, or in some cases, far longer. In the language of networks, they are the storage nodes, the repositories of quantum information. Teleportation into and out of atomic ensembles is therefore a critical step. In such systems, the state of a single photon can be imprinted onto a cloud of atoms, absorbed into the collective vibrations of electrons, and later retrieved. When teleportation transfers a quantum state from light to matter, it bridges two worlds, the mobile and the stable. Experiments have shown that photons can deliver their fragile states into atomic ensembles, separated by meters or more, and that those states can later be recalled with fidelity high enough to prove the principle. Each success moves teleportation closer to being a practical tool. The difficulty lies in the precision required. Atoms in an ensemble are never perfectly identical. They vibrate, they drift, they interact with one another and with the environment. To make them act as a single chorus requires cooling, shielding, and control of extraordinary delicacy. Even then, decoherence threatens to erode the stored state. Scientists combat this with clever protocols, using entanglement swapping and error correction to refresh and preserve the information. Progress has been steady, with coherence times stretching longer and fidelities improving year by year. Beyond ensembles, researchers have sought to teleport states between distant trapped ions or atoms in separate traps. These experiments represent the next step, linking matter to matter directly across space. Instead of photons flying freely, the states of ions are transmitted by entangling them with photons, sending the photons away, and then using the shared entanglement to complete teleportation between ions. The process is intricate, requiring hybrid systems that blend the mobility of light with the stability of matter. But when it works, it demonstrates that teleportation can bind distant atoms into a single quantum fabric. The implications are profound. If teleportation between atoms and photons can be scaled, it creates the foundation for quantum repeaters, the devices that extend entanglement across long distances. By storing states temporarily and then refreshing them, repeaters can stitch short entangled links into networks that span continents. Without them, teleportation would remain limited by losses and decoherence. With them, a quantum internet becomes possible. There is also symbolic weight in these experiments. To teleport photons is to move light. To teleport atoms is to move matter's quantum essence. The step from light to matter feels like a deepening of the dream, a shift toward the teleportation of the tangible. Of course, no atoms themselves are flying across space. Only their states are transferred. But those states define the atoms in their most essential way. In quantum mechanics, identity is not a physical shell, but the state itself. To teleport that state is, in a very real sense, to teleport the atom. Each demonstration is a reminder of how extraordinary the journey has been. From a theory written on paper in 1993, teleportation has advanced to the transfer of states between photons, ions, and atomic ensembles. The process remains fragile, but the path is clear. The next frontier lies in molecules, systems richer than single atoms, carrying more complex information and hinting at the vast challenge of teleporting life's building blocks. The step from atoms to molecules is more than a matter of scale. Molecules are not simply larger versions of atoms. They are assemblies of atoms bound together in intricate geometries, vibrating, rotating, and carrying within them vast amounts of quantum information. To teleport the state of a molecule is to move not only the essence of a single particle, but the orchestration of many working in concert. The challenge multiplies, but so too does the significance. In principle, the process is the same. Entangle a system, perform the joint measurement, send classical results, and reconstruct the state at a distance. In practice, the complexity is daunting. A molecule's state is composed of many layers. Its electronic configurations, vibrational modes, and rotational states. Each must be accounted for if teleportation is to be faithful. The more degrees of freedom, the more fragile the state becomes, and the more easily decoherence creeps in. Still, progress has begun. Experiments have demonstrated the teleportation of certain molecular properties, showing that the leap from atoms to small molecules is not forbidden. The door, however narrow, is open. The importance of this cannot be overstated. Molecules are the building blocks of chemistry and biology. To teleport their states is to approach the realm where life's processes reside. No one imagines that complex biomolecules, let alone living organisms, will be teleported anytime soon. The sheer number of particles and interactions involved makes that challenge unimaginably vast. But the movement toward molecules reveals a direction. It shows that teleportation is not confined to light or single particles. It is creeping toward the tangible world we inhabit. Each success also teaches lessons about scaling. Teleportation of photons revealed the need for stable entanglement sources. Teleportation of atoms demanded cooling and isolation. Teleportation of molecules underscores the necessity of error correction and control at levels far beyond current technology. Every advance illuminates both the promise and the limits. It is as if nature allows us glimpses of what is possible, then demands payment in ingenuity before offering more. What is striking is how the dream reshapes itself at each step. Fiction promised the teleportation of people, entire bodies moved in an instant. Physics gives us photons first, then atoms, then molecules. Each step is humbler, but each step is real. The dream of teleporting a human remains far beyond reach, yet the gradual march from light to matter suggests that teleportation is not confined to fantasy. It is a spectrum, unfolding piece by piece as our technology improves. This progression raises an inevitable question. If photons, atoms, and molecules can be teleported, what about the human self? A person is not a handful of particles, but a vast collection, trillions upon trillions of atoms bound in the complex symphony of life. Could teleportation ever reach that scale? And if it could, would the result be the same person or a copy with the illusion of continuity? These questions move the story from physics into philosophy, from laboratory demonstrations into the essence of identity itself. From photons to atoms to molecules, teleportation has advanced step by careful step, each achievement more audacious than the last. Yet, all along, in the background of scientific papers and experimental triumphs, the same question lingers. Could a human being ever be teleported? It is a question both thrilling and unsettling, blending physics with philosophy, science with imagination. To even approach it requires confronting the staggering scale of what a human body is. A single human being is composed of roughly 10 to the power of 28 atoms. Each atom carries quantum states that describe its energy, position, spin, and countless other variables. To teleport a person would mean capturing the state of every one of those atoms with perfect fidelity, transmitting that information, and reconstructing it in the exact same arrangement. The sheer amount of information involved defies comprehension. If one attempted to scan each atom even in a billionth of a second, the process would take longer than the age of the universe. The challenge is not merely difficult, it is overwhelming. Even if one imagined some miraculous device capable of this measurement, the rules of quantum mechanics impose further barriers. The no-cloning theorem forbids perfect copying of unknown quantum states. This means that to teleport a human, the original would have to be destroyed. As the information is extracted, what arrives at the destination would not be a duplicate, but the only version, the original erased in the process. This destruction is essential for teleportation to obey the laws of physics, but it raises a chilling question. If the original is destroyed and the copy created elsewhere, is the person who emerges truly the same, or simply an identical replica? The difficulty is not only technical, but philosophical. Identity is not just the arrangement of atoms. It is the continuity of experience, the unbroken stream of consciousness that makes one feel like oneself. Teleportation, by its very nature, interrupts that continuity. The original consciousness is annihilated, and a new one begins at the destination. To an outside observer, nothing seems amiss. The teleported individual speaks, remembers, and acts as though they are the same. But from the inside, from the perspective of the original mind, what becomes of awareness when the state is destroyed? Does it continue seamlessly, or does it end, replaced by a twin who only believes it has continued? These questions haunt the idea of teleporting the self. Physics tells us how to move states. Philosophy asks whether those states, when applied to the human brain, carry the essence of personhood. Some argue that identity is nothing more than the information encoded in neural patterns. If so, then teleportation recreates the self perfectly, and the person who steps out at the other end is indistinguishable from the one who stepped in. Others argue that continuity of consciousness matters, that a gap or interruption means the self has been lost, and only a convincing copy remains. Thus, the prospect of teleporting a human divides into two problems. The first is technological, the inconceivable challenge of capturing and reconstructing the quantum state of trillions of atoms. The second is philosophical, the unresolved question of whether the self can survive destruction and recreation. Even if one day the first problem is solved, the second may remain forever. When people imagine stepping into a transporter, they rarely consider the crushing load of information such a process would demand. A human body is not only composed of 10 to the power of 28 atoms, but arranged in patterns of staggering complexity. The brain alone contains on the order of 100 trillion synaptic connections. Each of these connections changes from moment to moment, reflecting thoughts, memories, and emotions. To teleport a person is to capture not just the static arrangement of matter, but the dynamic state of a living brain, with every flicker of electrical activity preserved. If one attempted to store this information, the numbers explode. Estimates suggest that recording the quantum states of all the particles in a human body would require more data than could be stored in all the computers on Earth combined, multiplied many times over. Even if such storage were possible, the transmission of that information would take astronomical timescales. To send the data through a channel moving at the speed of light might still take longer than the lifetime of the universe. In this sense, the barrier is not only physics, but sheer scale. Teleportation of humans does not merely stretch technology, it annihilates it. And yet, thought experiments persist because they reveal something about our ideas of selfhood. Imagine a perfect device that could perform this impossible scan and transmit the information flawlessly. You step into the chamber, your body is vaporized, the quantum states recorded and sent. Moments later, on a distant planet, the reconstruction begins. An exact version of you emerges, with all your memories, your personality, even the unfinished sentence you were about to speak. To those around, there is no difference. But to the you who was destroyed, is there continuity? Did you awaken on the other side? Or did you end, leaving behind a twin who only believes they are you? This dilemma echoes the ancient thought experiment known as the ship of Theseus. If every plank of a ship is replaced, piece by piece, is it still the same ship? If the old planks are reassembled elsewhere, which is the real one? In teleportation, the planks are not wood, but atoms, and the reconstruction is instantaneous. The paradox is sharper because consciousness is involved. It is not only the identity of objects, but the essence of awareness that is at stake. Star Trek famously sidestepped the issue, treating teleportation as seamless. Characters stepped onto the transporter pad and reappeared elsewhere, continuing their lives without pause. But philosophers and physicists alike have questioned what this really means. If continuity is preserved, teleportation is miraculous. If it is not, then each use of the transporter is a quiet death, with a copy walking away believing it survived. The horror is hidden in plain sight. What makes the question so powerful is that it cannot be resolved by experiment. To the outside world, the teleported person is indistinguishable from the original. They carry the same memories, the same habits, the same sense of self. The only perspective that could reveal the truth is that of the original consciousness, and if it is destroyed, it has no voice to speak. Thus, the issue remains forever hidden, an unanswerable riddle at the heart of the dream. The unresolved paradox of teleporting a human self reveals that the challenge is not only one of engineering, but of meaning. Physics may one day provide methods to scan, transmit, and reconstruct matter on scales greater than we can now imagine. But whether such a process preserves the essence of identity remains a deeper question. In many ways, the debate mirrors the mystery of consciousness itself. We do not yet understand why a collection of neurons gives rise to awareness. We do not know why the electrical activity of the brain is accompanied by the inner experience of thought and sensation. Without this understanding, the question of whether teleportation preserves the self is as elusive as the question of what the self truly is. Some argue that continuity is irrelevant, that the self is nothing more than the information encoded in the brain's structure. By this view, if a copy carries every memory, every habit, every subtle detail of personality, then it is the same person. The original is gone, but in every practical sense, the individual continues. Others insist that something essential is lost, that awareness is not reducible to information alone. They argue that a break in continuity, however brief, is equivalent to death. The being who steps out of the teleporter is not the same, but a new consciousness inheriting the story of the old. This conflict is not only academic, it touches on fears and hopes that cut to the core of human existence. If teleportation one day becomes technologically possible, would people use it? Would they step willingly into a machine that promises to recreate them elsewhere while annihilating the original? Would society accept the continuity of copies as genuine, or would a shadow of doubt remain, leaving teleportation haunted by the suspicion of quiet replacement? The thought is unsettling. Yet it also illuminates why teleportation grips the imagination so fiercely. It forces us to confront what it means to be alive, what it means to be a person, and what it means to endure. Our myths of teleportation are not only about convenience or conquest of distance. They are about the desire to escape limitation, not only of space but of mortality itself. To teleport is to deny boundaries, to say that distance and destruction do not end us. But whether that denial is truth or illusion remains unanswered. For now, teleportation of the self remains a dream far beyond reach. The technical barriers are astronomical and the philosophical puzzles unresolved. Yet the very act of considering it changes us. It forces science to probe deeper into information and consciousness, and it challenges philosophy to refine its understanding of identity. It reveals that teleportation is not only a technological project, but a mirror reflecting humanity's oldest questions. As we turn from the question of the self to the broader horizon, a new possibility emerges. Even if humans cannot be teleported, entanglement and teleportation may play another role, one that speaks not to bodies, but to exploration. In the vastness of space, where distances stretch beyond lifetimes, teleportation offers a different gift: the ability to communicate securely and instantly across cosmic frontiers. In this sense, the dream of teleportation does not end with the self. It expands outward toward the stars. When we lift our gaze from Earth to the night sky, the dream of teleportation takes on a new dimension. The stars burn at distances so great that even light, racing at 300,000 kilometers per second, takes years, centuries, or millennia to reach them. To travel there in bodies of flesh and blood seems hopelessly beyond our reach. But communication, the lifeline of exploration, is just as daunting. Even if spacecraft could one day journey to distant planets or other stars, the signals they send back would arrive only after long delays. In this vastness, teleportation offers not the fantasy of beaming ourselves across the galaxy, but the profound possibility of keeping in touch across cosmic gulfs. The key lies in entanglement. If two particles can remain linked across distance, then in principle that link could extend far beyond Earth. A pair of entangled photons, one carried on a spacecraft and the other kept on Earth, remain bound no matter how far apart they drift. When one is measured, its partner responds instantly, as if distance were irrelevant. To explorers scattered across the solar system, such threads of entanglement could become lifelines, connecting them to home in ways that ordinary signals cannot. It is important to be precise. Entanglement does not allow faster than light communication. The correlations between particles appear instantly, but the results remain random until compared through classical channels. No message can be smuggled through entanglement alone. Yet the combination of teleportation and entanglement offers something extraordinary. It allows quantum states to be transferred securely across vast distances, with a level of protection that classical communication can never achieve. An eavesdropper attempting to intercept or tamper with entangled particles would be exposed immediately, for the delicate correlations would collapse. In this way, teleportation becomes a foundation for quantum secure communication, a treasure for interstellar explorers. Imagine a future where spacecraft leaving Earth for Mars or beyond carry with them entangled pairs linked to stations at home. As they voyage outward, these links serve as conduits for teleporting quantum states. Messages still require classical channels to complete the process, but those channels are shielded by the integrity of entanglement. No enemy, no accident, no disturbance can read them without detection. Communication in the cosmos becomes not only possible, but unbreakably secure. Already, experiments have hinted at this future. The Mischur satellite proved that entanglement can survive between orbit and Earth, across distances of more than 1,000 kilometers. If entanglement can endure such a leap through atmosphere and space, why not across millions of kilometers to Mars, or even farther? The challenge is technical, but the principle is sound. What has been achieved between mountaintops and satellites may one day be achieved between planets and stars. The vision of using entanglement for space exploration reveals a striking truth. Teleportation in this context is not about transporting matter, but about transporting trust. When messages are sent across deep space using classical methods alone, they can be intercepted, corrupted, or delayed. With teleportation protocols, the quantum state itself carries the guarantee of integrity. No one can tamper with an entangled channel without being noticed. In this sense, teleportation becomes the most secure handshake the universe allows, binding distant travelers and their homeworld in a bond no adversary can break. This promise grows more profound the farther we look. A voyage to Mars would already involve delays of minutes in ordinary communication, depending on the alignment of planets. A journey to Jupiter or Saturn would extend those delays to hours. For interstellar travel, the delays stretch into years or centuries. Teleportation cannot erase these delays because classical communication remains bound by the speed of light. But it can redefine what those communications mean. Instead of fragile radio signals vulnerable to interference, messages could be encoded in the states of entangled particles, ensuring fidelity across cosmic gulfs. The time may not be shortened, but the connection becomes absolute. The thought is both humbling and inspiring. We often imagine teleportation as instant presence, bodies dissolving on Earth and rematerializing on distant worlds. But perhaps the first use of teleportation in space will not be to send explorers themselves, but to send the essence of their communication. This is no less miraculous. For civilizations separated by light years, the ability to share information without fear of distortion may prove more valuable than the ability to transport matter. Teleportation becomes a bridge of meaning rather than a bridge of flesh. There is another dimension to consider. Entanglement does not weaken with distance, at least not in principle. If two particles are created in a shared state and then carried apart, their connection remains. They do not fade or fray simply because they are separated by kilometers or even light years. What limits us is not nature but technology, the difficulty of preserving entangled particles against decoherence and loss. If those technical barriers can be overcome, then the threads of entanglement could weave across the galaxy. Imagine starships leaving Earth with caches of entangled particles linked to their homeworld, carrying with them invisible threads that tie them forever to their origin. The implications ripple outward. Entanglement could provide not only communication but also synchronization. Quantum states are exquisitely precise. Teleportation could allow distant spacecraft to coordinate their clocks and instruments with fidelity beyond classical limits. Navigation, science, and exploration would all be strengthened by this hidden unity. It is as if entanglement provides a secret nervous system for a civilization spread across the stars, allowing it to act as one organism even across the gulfs of space. This reframing of teleportation is crucial. It reminds us that the dream does not end with the disappointment of not transporting bodies. It transforms into something more subtle, but perhaps more powerful. Teleportation becomes the foundation of a cosmic web of communication, binding explorers and worlds into a single network. The stars remain distant, but their separation becomes less absolute. To imagine entanglement extended across interstellar distances is to glimpse a future where teleportation changes the very meaning of exploration. Today, when we send probes to the edge of the solar system, their signals take hours to return. If humans one day voyage beyond those horizons, their words to Earth would be delayed by months or years. Entanglement cannot eliminate that delay, but it can ensure that every message that arrives carries the mark of authenticity, untouched by interference. The first great gift of teleportation in space may not be speed, but certainty. There is a poetic symmetry here. For centuries, sailors relied on fragile lines of communication across oceans. Letters carried by ships took weeks to reach home, and the uncertainty was as great as the distance. Families often did not know if their loved ones still lived. In the cosmic age, the scale grows immeasurably larger, but the yearning is the same. Entanglement, harnessed through teleportation, offers a way to reduce that uncertainty. Even if the journey is long, even if the signals take years, the explorers and those on Earth will know that what they share is secure, untarnished, and true. This vision inspires physicists to plan experiments beyond Earth. Future missions may test entanglement between satellites and spacecraft on deep space trajectories. Entangled photons could be distributed between Earth and the Moon, then Earth and Mars, building step by step a solar system-wide web of correlations. Each experiment would face challenges of alignment, loss, and decoherence, but each would also push the limits of possibility. Just as the Messier satellite proved that teleportation could work between orbit and ground, new missions could prove that it can stretch across millions of kilometers. The symbolism of such achievements cannot be ignored. If entanglement threads can reach between planets, then humanity itself becomes more connected than distance would suggest. Teleportation in this sense is not about defying space, but about revealing that space is not as absolute as it appears. Beneath the visible structure of the cosmos lies a hidden fabric of correlation, a web that ignores separation. By learning to weave with that fabric, explorers may one day carry the comfort of connection with them, no matter how far they travel. Perhaps this is the true destiny of teleportation in the context of space. It may never beam bodies across the stars, but it may create a new kind of presence, a unity of information and trust that spans the galaxy. The dream of teleportation thus transforms again. It is no longer about flesh moving through beams of light. It is about civilization extending itself without losing coherence. It is about explorers journeying into the dark without losing their voice. As we close this chapter, the story of teleportation stands at a threshold. From photons to atoms, from laboratories to satellites, from Earth to the imagination of interstellar travel, it has grown in scope and ambition. The next chapter turns to the deeper structure of this progress, to the frontier of quantum information itself. For teleportation is not an isolated phenomenon. It is a cornerstone of a much larger edifice, a vision of networks, repeaters, and entanglement swapping that may one day bind not only planets, but civilizations into a single quantum whole. Teleportation began as a daring idea on paper, then became a fragile demonstration in laboratories, and now it points toward networks that may one day encircle the planet and extend into space. To understand its future, one must see teleportation not as an isolated phenomenon, but as a cornerstone of a larger revolution, the rise of quantum information. Just as the invention of the telegraph once shrank the world, and the internet later reshaped civilization, the mastery of entanglement and teleportation could herald an entirely new era of communication and computation. At the heart of this revolution is the recognition that information itself can be quantum. In the classical world, information is stored in bits, each either 0 or 1. In the quantum world, information is stored in qubits, which can exist in superpositions of 0 and 1, entangled with one another in webs of correlation richer than any classical system can contain. The power of quantum information lies not in speed alone, but in structure. Entangled qubits can solve problems and process data in ways that classical bits cannot, exploring multiple pathways simultaneously and binding results together in non-local patterns. Teleportation becomes the mechanism by which these qubits can move. not by copying but by transferring. In a classical computer network, information is duplicated endlessly, packets of data flying from one server to another. In a quantum network, duplication is forbidden by the no-cloning theorem. Teleportation replaces copying with destruction and recreation, ensuring that quantum information can travel without violating the rules of physics. This makes teleportation the fundamental transport protocol of the quantum age, the invisible courier that carries qubits from one place to another. But building such networks requires more than isolated demonstrations. Entanglement must be extended across long distances, and this is where the concept of entanglement swapping comes into play. If two pairs of entangled particles are created, and one particle from each pair is brought together and measured, the two remaining particles, which never interacted, become entangled. This remarkable process allows entanglement to leap across gaps, chaining shorter links into longer ones. It is the principle behind quantum repeaters, devices that promise to stretch entanglement across continents and eventually planets. The vision of a quantum internet emerges from these principles. Imagine nodes of atoms and photons, linked by entanglement, able to teleport states back and forth with perfect fidelity. Such a network would allow unbreakable cryptography, distributed quantum computing, and synchronization of clocks with accuracy beyond anything achievable today. It would be a new nervous system for civilization, operating not with radio waves and wires, but with the hidden threads of the quantum world. The progress already made is striking. Laboratories have demonstrated entanglement swapping, teleportation across cities, and entanglement between satellites and ground stations. Quantum repeaters are being developed to extend these results further. Each step brings the vision closer. It is as if we stand in the mid-19th century of the quantum age, with the telegraph wires just being strung, the first messages being tapped across them, and the vast potential of global communication only beginning to dawn. The promise of quantum networks rests on solving the problem of distance. In ordinary communication, signals weaken as they travel, amplifiers boost them, but in the quantum world, amplification is impossible without destroying the delicate states. This is where teleportation becomes indispensable. Instead of amplifying, one can extend entanglement step by step through a chain of nodes, teleporting quantum states from one station to the next. The process does not copy the state, but relays it, each handoff preserving the integrity of the information. Quantum repeaters are the devices designed to make this possible. At each node, entangled particles are stored in quantum memories, their states preserved until the next link is ready. Entanglement swapping connects the segments, creating a continuous thread across long distances. Classical signals coordinate the process, ensuring that the fragile states are transferred with fidelity. In this way, teleportation transforms from a laboratory demonstration into an infrastructure, the backbone of a future internet, woven not from copper and fiber alone, but from entangled particles spanning continents. The implications of such an internet are profound. Communication could be made absolutely secure, for any attempt at eavesdropping would collapse the entanglement and reveal intrusion. Distributed quantum computing could allow machines separated by oceans to work together as if they were side by side, solving problems too vast for any single computer. Clocks separated by thousands of kilometers could be synchronized with precision, measured not in milliseconds, but in billionths of a second, revolutionizing navigation and science. The reach of teleportation expands from the realm of curiosity into the realm of necessity. What is most striking is how naturally teleportation fits into this architecture. In classical networks, the transfer of information is trivial. In quantum networks, transfer is the challenge, and teleportation is the answer. It is the only method that allows qubits to move without cloning, without error, and without betraying their nature. Teleportation is not an add-on, It is the central artery. Without it, the dream of a quantum internet collapses. With it, the dream takes shape. The early steps toward this dream have already been taken. Experiments in Europe, China, and North America have demonstrated entanglement distributed over metropolitan areas, connecting laboratories through networks of fiber optic cables. Satellites have carried entangled photons across thousands of kilometers, laying the foundation for global links. Quantum memories have stored entangled states long enough to prove that repeaters are possible. Each success is a piece of a puzzle, fitting together into the image of a network that could one day wrap around the planet. There is a sense of déjà vu in this progress. In the 19th century, when the first telegraph lines were strung, few could imagine that within decades cables would cross oceans. When the first computers were connected by experimental networks in the mid-20th century, few foresaw the internet transforming every aspect of life. Teleportation today stands at a similar threshold. It is young, fragile, and limited. But its trajectory points toward a future where quantum networks may define a new era of civilization. If teleportation becomes the transport protocol of a quantum internet, then the question naturally follows: how far can such a system extend? On Earth, we imagine networks linking cities, countries, and continents. But there is nothing in principle that prevents quantum networks from stretching across the solar system, and perhaps far beyond. The only obstacles are technical, not fundamental. If entanglement can be distributed, refreshed, and stored, then teleportation can bind together worlds separated by millions of kilometers. This prospect invites speculation about what future civilizations might achieve. If humanity survives long enough to spread among the stars, teleportation may become the hidden architecture that keeps such a civilization coherent. Star systems separated by light years could exchange information not through vulnerable radio signals, but through teleportation protocols woven into vast quantum networks. Classical communication would still take years to cross the gulfs, but the security, fidelity, and precision of the messages would be absolute. Entire starfaring societies could depend on teleportation as their nervous system, invisible but essential. Even more radical visions emerge when we consider the possibility that teleportation might scale to systems far beyond single qubits. Perhaps advanced civilizations have learned to teleport not only particles, but macroscopic quantum states, structures larger than anything we can now imagine. If so, their networks may be incomprehensibly powerful, weaving together matter and information across cosmic distances. To us, teleportation remains fragile, confined to photons and atoms. To them, it might be as ordinary as electricity, an unseen force powering every aspect of existence. What unites these possibilities is the recognition that teleportation is not an end in itself, but part of a larger whole. It is a tool that allows quantum information to move, a mechanism that turns entanglement from a curiosity into a utility. The future of teleportation is therefore inseparable from the future of quantum information. Each advance in repeaters, memories, and error correction strengthens the foundation. Each success in extending entanglement pushes the horizon farther. And yet, there is humility in this vision. Teleportation does not break the laws of physics. It does not erase distance or bend time. It works within the limits of causality, preserving the sanctity of the speed of light. Its power comes not from defiance, but from ingenuity, from finding ways to use the strangeness of entanglement without shattering the consistency of the universe. This balance may be the reason it holds such fascination. It is miraculous, but lawful. It is alien, but real. As we close this chapter, teleportation stands revealed as more than a trick of quantum mechanics. It is a pillar of the quantum age, a process that could shape the future of communication, computation, and civilization itself. The question that remains is the deepest of all. Is entanglement the key not only to networks and information, but to the ultimate dream of teleportation itself? The final chapter turns to that question, weighing what has been achieved against what has been imagined, and asking what entanglement truly means for the human desire to transcend distance. For centuries, teleportation belonged to myth. It was a story told in magic and religion, a power granted to gods and heroes, but denied to mortals. Then came the age of science fiction, when transporters shimmered on screens and characters walked effortlessly across the stars. These images shaped the human dream of instantaneous travel, embedding teleportation in our collective imagination. Yet always, the gap between fantasy and physics loomed vast, until entanglement. Entanglement is the first real tool that makes teleportation possible, not as a metaphor or illusion, but as a process tested in laboratories and measured with instruments. It does not beam bodies from place to place. It does not allow faster than light journeys, but it does something subtler and perhaps more profound. It allows the essence of a particle, its quantum state, to vanish in one location and reappear in another. That essence is not matter, but in the quantum world, the state is everything. This is the strange gift of entanglement. It reveals that the universe is more connected than our senses suggest. Where we see separation, entanglement insists there is unity. Where we assume distance matters, entanglement whispers that it does not. Teleportation harnesses this hidden unity, using it to transfer information across space without moving particles themselves. It is not the teleportation of fiction, but it is real, and its reality demands that we reconsider what teleportation means. What we find is a tale of both triumph and humility. Triumph because teleportation of photons, atoms, and even molecules has been demonstrated. Distances extended from meters to thousands of kilometers, and entanglement distributed from Earth to orbit. Humility because each success is bounded by the limits of decoherence, the requirement of classical communication, and the impossibility of transmitting matter itself. The dream is alive, but it is transformed. Perhaps the true achievement of teleportation is not in transporting matter, but in transporting trust. In a future quantum internet, teleportation will guarantee communication that is secure, untouchable, and unbreakable. In space exploration, it may bind astronauts and their homeworld in links that distance cannot corrupt. For civilizations more advanced than ours, it may become the nervous system of society stretched across stars. The dream shifts from bodies to bonds, from travel to connection. And yet, even in this transformed vision, a haunting question remains. Is entanglement the key to the teleportation we imagined? Can it ever bridge not only states of light and matter, but the human self, the consciousness that wonders and dreams? Or is teleportation destined to remain a process of information alone, never reaching the realm of flesh and awareness? The answer lies in the balance of what entanglement allows and what it denies. Entanglement has already redrawn the boundary between what is possible and what was once unthinkable. Before the 1990s, teleportation was a fantasy. After the 1990s, it was a protocol. By the 2010s, it had become a planetary experiment, photons leaping across mountains and orbit. Today, it stands as the backbone of quantum communication. Yet when we ask whether entanglement is the key to teleportation in its fullest sense, we must face what it cannot do. First, entanglement does not move matter. A teleported particle is not the same physical particle that once existed elsewhere. Its state is recreated in a partner particle, while the original is erased. For photons, ions, or atoms, this is enough. For human beings, it is another matter entirely. The body is not just a set of atoms. It is a dynamic system of unimaginable complexity, each cell buzzing with biochemical processes, each neuron firing in intricate patterns. To teleport such a system would mean recording and recreating states with a fidelity beyond comprehension. Entanglement gives the principle, but the scale is overwhelming. Second, entanglement does not defy relativity. The requirement of classical communication ensures that no teleportation occurs faster than light. The dream of instantaneous journeys across galaxies, the kind that fiction so often portrays, remains closed to us. Even if teleportation of humans were technically possible, the signal carrying the necessary measurement results would crawl at the same speed limit that binds every form of communication. Entanglement shows us unity beyond space, but it does not let us cheat time. Third, entanglement does not answer the question of consciousness. Teleportation of atoms and molecules transfers states, but whether the self can be teleported remains an enigma. Identity may be nothing more than information, or it may be tied to continuity of awareness, something entanglement cannot preserve. A teleported person may walk and speak as if unchanged, but the original consciousness may have ended. Entanglement carries information, but it does not carry the certainty of selfhood. These limits do not erase the wonder of teleportation, they refine it. They tell us that entanglement is the key to a new kind of teleportation, one not of bodies, but of information, not of instant travel, but of perfect trust, not of consciousness, but of communication. It is a key that opens doors we never expected, doors to secure networks, to interplanetary coordination, to the possibility that civilizations separated by light years could still remain bound. And yet, there remains a tantalizing thought. Perhaps entanglement is not the final word, but the first whisper of something deeper. Some physicists suspect that space-time itself emerges from entanglement, that the geometry of the cosmos is woven from invisible correlations. If this is true, then teleportation is not merely a trick within the universe, but a glimpse of the loom upon which the universe itself is woven. To master entanglement might be to master the very threads of reality in ways we cannot yet conceive. When we pause to consider the possibility that space-time itself arises from entanglement, the meaning of teleportation expands beyond anything once imagined. In ordinary experiments, we see teleportation as a tool, a way of transferring a state from one place to another. But if space is built from entanglement, then teleportation is not merely a trick within space. It is a glimpse into how space itself is stitched together. In that light, teleportation is not only about connection across distance, it is about revealing that distance may be an illusion, a byproduct of correlations too deep for our senses to perceive. Modern physics hints at this in theories like ADS-CFT, where the geometry of a higher dimensional universe emerges from patterns of entanglement on a lower dimensional boundary. Wormholes, once the realm of pure speculation, may be nothing more than entangled systems viewed through the lens of space-time. If this vision proves true, then teleportation is not simply a transfer of information. It is a demonstration of how entanglement bends the structure of reality itself. Each experiment in a laboratory may be a small echo of cosmic architecture, a human-scale rehearsal of the universe's hidden design. This view transforms the dream of teleportation. Instead of seeing it as a technology for travel, we might see it as a technology for unveiling. Each state that leaps across space shows us that separation is less fundamental than we thought. Each entangled particle whispers that the universe is more unified than our maps of space and time suggest. Teleportation becomes not only a process, but a metaphor, an illustration of a cosmos where the deepest connections are invisible yet unbreakable. There is beauty in this reimagining. Humanity longed for teleportation as a way to conquer distance, to shorten journeys and erase delays. Entanglement offers a subtler victory. It tells us that distance is not the prison we imagined. The threads of entanglement tie the universe together beneath the surface, ignoring the boundaries our eyes insist upon. When we teleport a photon's state from one mountaintop to another, we are not bending rules. We are touching the threads that hold the world together. And perhaps, in some far future, mastery of those threads may lead to powers we cannot yet describe. If space-time truly emerges from entanglement, then to manipulate entanglement on vast scales may be to reshape space-time itself. Teleportation, then, may not only be a tool for communication, it may be a rehearsal for engineering reality, a primitive gesture in a language that could one day rewrite the cosmos. But for now, we remain at the threshold, aware only of glimpses. What entanglement gives us today is enough to transform science, communication, and philosophy. It has already changed how we see distance and how we imagine connection. Whether it will one day change how we live and travel remains unknown. The dream of teleportation may never fully match the fantasies of fiction. Yet, in showing us the deeper unity of the universe, entanglement may prove to be a key to something greater than we ever dreamed. The story of teleportation begins in myths of gods and magicians, passes through the shimmering beams of science fiction, and arrives at last in the laboratories of our world. Along the way, it transforms. The teleportation of fiction promised instant journeys, bodies dissolving into light and reassembling across galaxies. The teleportation of physics gives us something different, yet no less wondrous. It gives us the transfer of states, the movement of identity without matter, the revelation that distance is not as absolute as we once believed. Entanglement is the thread that makes this possible. Without it, teleportation is fantasy. With it, teleportation is fact. It has been proven in photons, extended to atoms, whispered into molecules. It has been carried across rivers, stretched through optical fibers, sent between mountaintops, and even leapt between Earth and orbit. Each demonstration is a marker on the journey, proof that the impossible has become real. And yet, entanglement also sets the boundaries. It demands classical communication, ensuring no leap faster than light. It demands destruction of the original, enforcing the no-cloning theorem. It demands fidelity beyond our current reach, making the teleportation of humans an almost unimaginable challenge. In these boundaries lies the truth. Teleportation is not magic, but science, a process bound by the laws of the universe. Still, within those boundaries lies a miracle. The ability to move a quantum state across space without moving the particle itself is a glimpse into a universe more connected than it appears. It is a reminder that the surface of reality hides deeper threads, invisible but binding. To master those threads, even in part, is to step closer to understanding the hidden architecture of the cosmos. Perhaps we will never beam ourselves across the stars. Perhaps the dream of stepping into a transporter and emerging on another world will remain fiction. But entanglement has given us something no less valuable. It has given us secure communication, a new foundation for technology, and a vision of unity that transcends distance. It has shown us that teleportation, even in its humbler form, is real. As we stand at the threshold of the quantum age, we can see both the triumphs already achieved and the horizons still hidden. Entanglement may never carry our bodies, but it carries our imagination, our information, and our sense of connection. It whispers that the universe is more intricate and intimate than space and time alone can describe. In that whisper lies the true gift of teleportation. Entanglement may not beam us across the galaxy, but it shows us that we were never as separated from it as we thought. The universe is tied together in ways we are only beginning to glimpse. And in those hidden ties, perhaps, lies the first key to a teleportation grander than any dream. Not the conquest of distance, but the discovery of connection at the deepest level of reality.